All right, buckle up. Number 10. Gliese 667cc, the super-Earth under 3 suns. On November 21, 2011, astronomer Guillaume and Glaude Escude stepped in front of a microphone and described a planet that sounded like it came straight out of a Hollywood script. Just 24 light-years away, tucked inside the constellation Scorpius, sits a planet 4.5 times the mass of Earth, sitting squarely in the habitable zone of a red dwarf star. But here's the part that breaks your brain. That star doesn't fly solo, it's one piece of a triple star system. If you were standing on the surface of Gliese 667cc, you wouldn't look up and see one sun, you'd see 3. But the alien sky isn't even the most unsettling part. This world orbits its host star in just 28 days, sitting at a distance of only 0.125 astronomical units, closer than Mercury gets to our own sun. That kind of proximity almost certainly causes tidal locking, meaning one face of the planet is cemented in permanent daylight, while the other side is sealed in eternal darkness. By every conventional standard, that temperature split should be catastrophic. It should make the planet completely incompatible with life. And yet, Gliese 667cc catches roughly 90% of the stellar energy Earth receives. The catch is that most of it arrives as infrared radiation rather than visible light. The entire world would be drenched in a permanent deep crimson twilight, dimmer than Earth's daylight, but warm enough to matter. If this planet holds a thick enough atmosphere, heat would redistribute from the scorching day side across to the frozen night side, carving out a survivable ribbon of conditions at the terminator, the razor-thin boundary between eternal day and eternal night. And here's what makes that terminator zone genuinely extraordinary. It would offer something Earth has never once provided in 4.5 billion years: perfect climate stability. No ice ages, no warming spikes, no seasonal chaos, no axial wobble throwing everything into disorder. The temperature at that terminator boundary would remain essentially locked for billions of years straight. If life ever took hold there, it would develop under the most environmentally consistent conditions imaginable. We spent centuries assuming Earth-like means better. Gliese 667cc is the first reminder that we need to rethink that assumption entirely. Number 9. Kepler-62F, the atmospheric paradox planet. On April 18, 2013, NASA announced the discovery of a 5-planet system 1,200 light-years out in the constellation Lyra. The outermost world of that system, Kepler-62F, orbits at the frozen outer fringe of its star's habitable zone, collecting only 41% of the solar energy Earth receives. At 1.5 times Earth's radius, every conventional climate model on the books predicted this thing was a solid ice ball, a lifeless, glaciated rock drifting through the cold black. Scientists filed it away and moved on. Then, in 2016, astronomer Awamawa Shields at UCLA dropped a paper that blew those conclusions apart. Her team's atmospheric modeling revealed something nobody had seriously entertained. If Kepler-62F maintains carbon dioxide levels just 3 to 5 times higher than Earth's atmosphere and carries even a modest amount of methane alongside it, the planet could sustain year-round liquid water. The greenhouse effect alone could convert what everyone dismissed as a frozen wasteland into a warm, temperate ocean world. No additional energy from its star required. What this finding does to our concept of habitability is genuinely alarming. For decades, scientists defined the habitable zone as a tidy band around a star where a planet receives sufficient energy for liquid water. Kepler-62F tears that definition apart. The actual habitable zone isn't just about energy input, it's about atmospheric composition. And atmospheric composition is something we currently cannot measure for the vast majority of exoplanets we've cataloged. Kepler-62F has an orbital period of 267 days, not much longer than Earth's year, but unlike our world, which lurches through ice ages, warm periods, and seasonal cycles driven by orbital tilt and eccentricity, this planet's climate would stay locked. Whatever temperature its atmosphere produces, it holds, stable for billions of years on end. And if our habitable zone calculations have been too conservative this whole time, if atmospheric chemistry can warm worlds we wrote off as too far and too cold, then the number of potentially habitable planets in our galaxy doesn't land in the millions, it lands in the tens of billions. How many warm ocean worlds have we already cataloged and dismissed simply because we assumed they were too frigid to matter? Number 8. TOI-700D, the test discovery with a hidden atmosphere. On January 6, 2020, at the 235th meeting of the American Astronomical Society in Honolulu, astronomer Emily Gilbert announced a discovery that reframed just how close a potentially habitable world might actually sit. NASA's TESS satellite, purpose-built for hunting for planets around the nearest, brightest stars in the sky, had locked onto an Earth-sized world a mere 101 light-years out, orbiting comfortably inside the habitable zone of a stable red dwarf star. TOI-700D checks in at 1.1 times Earth's radius, receives 86% of the solar energy we get from our sun, and wraps up a full orbit in just 37 days. What makes TOI-700D a genuine priority target isn't just what it is, it's what happened 3 years after we found it. In January 2023, the James Webb Telescope trained its instruments on this nearby world and picked up something unexpected: possible signs of an atmosphere. Early data suggested this Earth-sized planet might carry a protective gaseous layer, one potentially containing the building blocks necessary for life. The analysis is still ongoing, but that single hint of an atmosphere elevates TOI-700D from an interesting find to a front-of-the-line candidate. Climate models generate two radically different portraits of this world. In the first version, TOI-700D is entirely submerged, a global ocean world with no exposed land anywhere, where life would evolve beneath an endless sky of perpetual clouds. In the second version, it's a desert world, with water frozen into massive polar ice caps, liquid water confined to the narrow twilight zones where frozen terrain meets warmer ground. By every scenario, the same feature emerges: tidal locking, one permanent day side, one permanent night side, and a terminator zone running between them where conditions can stay moderate and stable in ways Earth's restless, wobbling climate never manages. No seasons, no ice age cycles, no mass extinction events triggered by environmental collapse. Earth's habitability is temporary and variable, a brief window in a constantly shifting story. TOI-700Ds could be effectively eternal, an unchanging world orbiting a star that'll keep burning long before our own sun has guttered out.
Number 7. Kepler-186F, the first true Earth twin in the habitable zone. On April 17, 2014, astronomer Elisa Quintana stood before the scientific world and announced something that genuinely shifted our understanding of our place in the universe. The Kepler Space Telescope had confirmed a planet 582 light-years away in the constellation Cygnus that was almost exactly Earth's size, 1.1 times our radius, orbiting squarely inside the habitable zone of its star. This was Kepler-186F, and it was the first time in all of human history that we had confirmed Earth-sized worlds can exist in the regions where liquid water is possible. What makes Kepler-186F a fascinating puzzle is how hard it pushes back against our comfortable assumptions about what habitability looks like. The planet orbits an M1-type red dwarf star, pulling in only 32% of the stellar energy Earth gets from the sun. Conventional thinking says that should make it a permanently frozen wasteland, an ice world so locked down it would make Antarctica look like the Bahamas. It sits at the outer boundary of its star's habitable zone, exactly where most scientists would expect nothing but glaciers, permafrost, and silence. But here's where our models start to crack. Kepler-186F's entire fate hinges on something we have absolutely no way to measure from 582 light-years away: its atmosphere. With sufficient greenhouse gases, perhaps only a few times the carbon dioxide concentration in Earth's own atmosphere, this supposedly frozen rock could sustain liquid oceans. It could be a temperate, sea-covered world where life quietly thrives beneath the dim, ancient red glow of its star. The planet could be alive, and we simply have no way to know from here. What the discovery of Kepler-186F locked in forever is this. Red dwarf stars, which account for roughly 70% of every star in our galaxy, are fully capable of hosting Earth-sized planets in their habitable zones. If even a fraction of those worlds maintain atmospheres thick enough to hold warmth, the number of potentially habitable planets in the Milky Way isn't in the millions, it's in the billions. We found the first Earth-sized habitable zone planet orbiting the single most common type of star in existence. The math on cosmic loneliness gets a lot worse from there. Number 6. Kepler-62B, the first confirmed habitable zone planet around a Sun-like star. On December 5, 2011, NASA confirmed something scientists had been chasing for decades, a planet orbiting inside the habitable zone of a G-type star, the same stellar class as our own Sun, located 620 light-years away in the constellation Cygnus. Kepler-62b completes one orbit every 290 days and receives about 25% more stellar energy than Earth does. Its host star burns at 5,757 Kelvin, compared to our Sun's 5,778 Kelvin. For all practical purposes, this planet orbits a solar twin. That's where the certainty ends and the mystery begins. Kepler-62b has a radius 2.4 times larger than Earth's, which drops it right into the fuzzy no-man's land between rocky super-Earth and mini-Neptune. We have zero measurement of its mass. The planet is too distant for radial velocity detection. No mass means no density calculation. No density means no way to determine what the planet is actually made of. More than 13 years after its discovery, we still cannot say with confidence what Kepler-62b actually is. The possibilities are wildly different from one another. If it's rocky with a thick atmosphere, it could be a super-Earth with oceans deeper than ours, where marine life thrives beneath cloud-choked skies. If it's a water world with minimal rock content, the entire planet could be blanketed by a global ocean hundreds of kilometers deep, with exotic high-pressure ice phases forming at the bottom and no exposed land anywhere on the surface. Or it could be a mini-Neptune, a gorgeous blue jewel in the sky that contains nothing but a slowly thickening poison atmosphere wrapped around a rocky core. Beautiful, completely uninhabitable. What the discovery of Kepler-62b locked in forever is this. Red dwarf stars, which account for roughly 70% of every star in our galaxy, are fully capable of hosting Earth-sized planets in their habitable zones. If even a fraction of those worlds maintain atmospheres thick enough to hold warmth, the number of potentially habitable planets in the Milky Way isn't in the millions, it's in the billions. We found the first Earth-sized habitable zone planet orbiting the single most common type of star in existence. The math on cosmic loneliness gets a lot worse from there. Number 5. LHS-114B, the super-Earth that just revealed its atmosphere. In April 2024, astronomer Charles Cailliau at the University of Montreal published findings that fundamentally changed how we think about a planet first detected 7 years earlier. The James Webb Space Telescope had examined LHS-114B, a super-Earth orbiting a red dwarf star just 49 light-years out, and picked up potential signs of a nitrogen-rich atmosphere. This wasn't a run-of-the-mill atmospheric detection. This was the possible discovery of a real protective gaseous layer wrapped around a rocky world in the habitable zone. Scientists had been hunting for exactly this around red dwarf planets for decades. LHS-114b is a heavyweight by Earth standards. It measures 1.7 times our radius and packs 6 times our mass, generating surface gravity approximately 1.3 times what we experience. Walking around on this world would feel like having a 40-pound weight strapped to your body at all times. Every single step would cost more. Every structure would need to be engineered tougher, Every organism would need to be physically adapted to a relentless, unforgiving gravitational pull. But that crushing gravity might be precisely the feature that makes LHS-114B better than Earth as a long-term home for life. Our planet is quietly hemorrhaging its atmosphere into space right now. Solar wind steadily strips away hydrogen. Helium bleeds off into the void. Over the next billion or 2 billion years, Earth's protective atmospheric envelope will thin down to the point where it can no longer do its job. LHS-114B's powerful gravitational grip could hold onto its atmosphere for far, far longer, extending habitable conditions billions of years past the point where Earth goes dark. And the star it orbits makes the deal even better. This red dwarf is an M4.5 class, and it's unusually calm, producing far fewer of the violent stellar flares that make stars like Proxima Centauri such hostile neighbors. The combination of gravitational atmospheric retention, stellar longevity, and low flare activity could hand any life on LHS-114B billions of extra years to evolve past whatever complexity we've managed to scrape together on this planet. We're working with a deadline. They may not.
Number 4. Kepler-452B, Earth's older cousin with 1.5 billion extra years. On July 23, 2015, NASA convened a press conference to announce what nearly every major outlet immediately branded Earth 2.0. Located 1,400 light-years away in the constellation Cygnus, Kepler-452b orbits a G2-type star, the exact same spectral classification as our own Sun. The host star burns at 5,757 Kelvin against our Sun's 5,778. The planet completes an orbit every 385 days, remarkably close to our 365-day year. It sits at 1.04 astronomical units from its star, almost perfectly mirroring Earth's orbital distance, and receives only 10% more stellar energy than we do. The surface comparisons are striking, but the most unsettling detail isn't any of the similarities. It's the age. Kepler-452's host star is 6 billion years old, making it 1.5 billion years older than our 4.6 billion-year-old Sun. If life exists on Kepler-452b and followed an evolutionary timeline even loosely parallel to Earth's, it had a head start of 1.5 billion years on us. When whatever civilization lives there was sitting at the technological level humanity occupies right now, Earth's continents were still barren, lifeless rock. Complex multicellular life hadn't emerged yet. The Cambrian explosion, the evolutionary event that gave rise to nearly every major animal body plan, was still hundreds of millions of years in the future. The oldest rocks on our planet hadn't even formed. Think about what humanity pulled off in just 10,000 years since the agricultural revolution. Cities, mathematics, medicine, space travel, global communication. Now stretch that forward by 1.5 billion years. What does intelligence become with that much runway? What understanding of the universe becomes available? What technologies stop sounding like science fiction and become mundane? The gap between us and any potential life on Kepler-452b isn't measured in centuries or millennia, it's measured in geological epochs. The planet's radius clocks in at 1.5 to 1.6 times Earth's, putting it right at the uncertain boundary between rocky super-Earth and gaseous mini-Neptune. We don't know its composition, its atmosphere, or its surface conditions with any certainty. But we know its star will stay stable for another 6 billion years, offering a total habitable window potentially twice as long as Earth's entire history. We're not looking at Earth's twin. We're looking at what Earth could become with more time, orbiting a star that offers that time in abundance. Number 3. Proxima Centauri b, the closest potentially habitable world. On August 24, 2016, astronomer Guillaume Anglada-Escudé stepped before the world and delivered a revelation that turned interstellar exploration from science fiction into an engineering problem. Our nearest stellar neighbor, Proxima Centauri, hosts a rocky planet inside its habitable zone. The distance is 4.24 light-years, close enough that a spacecraft traveling at 20% the speed of light could reach it within a single human lifetime.
Proxima Centauri b is not some distant dream requiring generation ships or centuries of suspended animation. It is reachable with propulsion technology we could plausibly build within this century. But proximity doesn't mean safe. Proxima Centauri is an M5.5 red dwarf, one of the most volatile types of stars capable of sustaining nuclear fusion. It generates flares 10,000 times more powerful than the largest solar flare ever recorded on our own sun. These eruptions hammer Proxima Centauri b with X-ray and ultraviolet radiation at levels 400 times higher than anything Earth has to endure. The planet orbits at just 0.05 astronomical units from its host, 20 times closer than Earth orbits the Sun, completing a full year every 11 days. At that distance, the stellar wind pressure it absorbs is 2,000 times stronger than what Earth faces. Everything in conventional science says Proxima Centauri b should be a radiation-scorched wasteland, its atmosphere stripped down to nothing eons ago, its surface sterilized by X-ray bombardment intense enough to shatter complex molecules on contact. And yet, some researchers have proposed something that flips the entire script. What if those flares aren't destroying any chance of life, but seeding it? High-energy radiation drives chemical reactions that are simply impossible in Earth's quieter, gentler environment. The relentless stellar bombardment could pour energy into exotic biochemistry, creating the molecular building blocks of life through reaction pathways that don't exist anywhere in our calm solar system. The planet is almost certainly tidally locked, one face permanently baked under the star, the other sealed in eternal cold. Between them sits the Terminator Zone, a band of perpetual twilight where temperatures might stay moderate despite the chaos surrounding it on all sides. Life evolving in that zone would never face Earth swings, no temperature extremes, no seasons, no climate chaos. It would develop under conditions of remarkable consistency, beneath a dim red star that will burn steadily for trillions of years, a stability Earth's variable, aging sun can never match. Number 2. TRAPPIST-1e, the Goldilocks planet in a 7-world system. On February 22, 2017, astronomer Michael Guillon announced something that had never been documented before in the history of astronomy. 40 light-years away in the constellation Aquarius, 7 Earth-sized planets orbit a single ultra-cool dwarf star designated TRAPPIST-1e. The entire system is packed so tightly that all 7 worlds fit within the orbital radius that Mercury travels around our Sun. The planets are so close to one another that standing on TRAPPIST-1e, you'd see neighboring worlds hanging in the sky as visible disks, not pinpoints of light, but actual planetary shapes, occasionally transiting across the dim face of the parent star. But the most disorienting detail isn't the number of planets or how close they orbit, it's the age. TRAPPIST-1e's host star is 7.6 billion years old, making it 3 billion years older than life on Earth has had for evolutionary runway. The fourth planet out, TRAPPIST-1e, sits perfectly inside the habitable zone. It measures 0.92 Earth radii and 0.69 Earth masses, with a density of 5.43 grams per cubic centimeter. It receives 66% of the stellar energy Earth pulls from the Sun, placing it in an optimal position for liquid water. By size and composition, it is the most Earth-like world ever confirmed. All 7 planets exist in near-perfect orbital resonance, their gravitational relationships locked into stable mathematical ratios that have held steady for billions of years. The system is ancient, organized, and enduring in a way our comparatively young solar system simply hasn't had time to be yet. In September 2023, the James Webb Space Telescope detected possible signs of atmospheric chemistry on some TRAPPIST-1e planets. The scientific debate over those readings is still loud, but what nobody disputes is the timeline. TRAPPIST-1e had 7.6 billion years of potential evolution. If life on TRAPPIST-1e followed a path even loosely similar to Earth's, it reached our current level of development while Earth was still a molten ball of rock with no solid crust, no complex life, no photosynthesis, no oceans capable of supporting anything beyond the most primitive chemical reactions.
If intelligence evolved on TRAPPIST-1e, it had 3 billion additional years to become something we currently don't have the intellectual framework to comprehend.
Number 1. K2-18b, the Hycean world with a possible biosignature. On September 11, 2023, astronomer Niku Madhusudan at the University of Cambridge published findings that sent genuine shockwaves through the global scientific community. The James Webb Space Telescope had analyzed the atmosphere of K2-18b, a planet 124 light-years away, and detected a molecular signature consistent with dimethyl sulfide. On Earth, dimethyl sulfide is produced exclusively by biological processes. No known geological mechanism, no atmospheric chemistry, no non-living process creates it in significant quantities. On our world, it comes from phytoplankton, microscopic marine organisms that anchor the base of ocean food chains across every sea on the planet. K2-18b has no business being habitable by any standard definition. It clocks in at 2.6 times Earth's radius and 8.6 times our mass, a mini Neptune that conventional planetary models classify as a gas dwarf, a small rocky core wrapped in a thick hydrogen-helium envelope. These worlds are textbook examples of environments incompatible with life as we understand it. But K2-18b refuses to be categorized neatly. In 2019, scientists detected water vapor in its atmosphere. Follow-up observations confirmed the presence of methane and carbon dioxide. The full atmospheric picture pointed towards something scientists had only recently given a name to, a Hycean world, a planet carrying a hydrogen-rich atmosphere sitting above a planet-wide liquid ocean. The surface conditions on K2-18b would be alien on a scale difficult to put into words. Atmospheric pressure could run into the hundreds of times Earth's sea level. The ocean might extend hundreds of kilometers deep before transitioning into exotic high-pressure ice phases that don't naturally form anywhere in our solar system. Surface temperatures could hover around 23 degrees Celsius, roughly 73 degrees Fahrenheit, warm enough to support liquid water despite the crushing weight of atmosphere above it. The dimethyl sulfide detection remains deeply controversial. Many astronomers argue the signal could be an instrumental artifact, misidentified molecules, or some form of unknown abiotic chemistry nobody has identified yet. The scientific community demands extraordinary evidence for extraordinary claims, and a single telescope reading doesn't meet that bar. Follow-up observations are in the pipeline. Independent analyses are actively underway. But if the detection holds, if dimethyl sulfide really is present in K2-18b's atmosphere, then we haven't just found a planet better suited for life than Earth. We found a planet where life already exists right now, thriving inside an environment completely unlike anything in our own solar system, proving that biology discovers pathways and exploits conditions we never imagined were survivable. The universe may be full of Hycean worlds, their thick hydrogen skies concealing oceans teeming with organisms we lack the imagination to picture, living on planets we dismissed as uninhabitable simply because they don't look anything like home.